Okay, let's move on to question 7. In 2000, 58% of females age 15 years of age and older lived alone, according to the U.S. Census Bureau. A sociologist tests whether this percentage is different today by conducting a random sample of 500 females aged 15 years of age and older and finds that 285 are living alone, 285 of the 500. Is there sufficient evidence at the alpha equals 0.1 level of significance to conclude that the proportion has changed since 2000? Use the classical approach. Okay, so the idea here of percentage points us to using the parameter P for the population proportion. And the idea of changed, is there sufficient evidence at the 0.1 level of significance to conclude that the proportion of females who live alone has changed since 2000? That's not equal to the standard, what it was in 2000. And then step 2 is to state alpha 0.1. Step 3 is to compute the test statistic, which is p hat minus p0, p0 1 minus p0 over the sample size. So p hat is x over n, 285 over 500, the sample size. .57. P0 is the standard. That's the percentage of females aged 15 years or older that lived alone in 2000, and that is 58%. And the sample size is 500. So let's plug in 0.57 minus 0.58 divided by square root of 0.58, 1 minus 58 over 500, and we approximately get minus 0.45. Step 4 is to find the critical values, since we're using the classical approach. So let's draw our picture, and we've got z alpha divided by 2 and minus z alpha divided by 2. And this region here is the critical region, and this region here is the critical region. And basically, all we have to do is look in table 5 to get z alpha by 2 and minus z alpha by 2. So let's go over here to table 5 and look at the 0.1 level of significance, which is right here, and we're dealing with a two-tailed test. So these are the critical values. 1.645. So this over here is 1.645 and this is minus 1.645. Now we move on to step 5, which is compare the test statistic with the critical values. Let's just write down the test statistic. And remember, I told you there was an easy way to do this. Is the test statistic, is this number here, minus 0.45, is it located in the red region? And it should be clear that it's not in the red region because it's right here, minus 0.45 is not in the red region. So the conclusion is we fail to reject, and that's step 6. Step 6, fail to reject. HO. Okay, one classic application of correlation involves the association between the temperature and the number of times a cricket chirps in a minute. Listed below are the numbers of chirps in 1 minute and the corresponding temperatures in degrees Fahrenheit. So that's what I've done. I've got a plot over here. Part A says create a scatter plot of the data. So we've got chirps per minute. And then over here we've got, on the y-axis, we've got degrees Fahrenheit. So you can see that as the number of chirps goes up, then the temperature tends to increase as well. So this is a positive linear relationship. And that's part B. Does there seem to be a linear correlation based on the scatter plot? Yes, a positive linear relation. Now part C is asking us to determine the linear correlation coefficient. And that's going to come from the printout down here. And the linear correlation coefficient is right here, so we just write that number down, 873,679. Okay, part D. Find the general equation of the regression line for the given data, and that's going to look like y hat equals b1 x plus b0. So b1, remember, is the slope and b0 is the y-intercept, and we're going to get these from the printout down here. So b1 is given by x variable 1, and then b0 here is given as the intercept. So let's go ahead and just plug in b1 and b0 into the equation above and see what we get. So we get y hat is equal to b1, which is 0.05 times x, plus b0, which is 27.63. And that's part D. Part E says predict the estimated temperature if a cricket chirps 1,000 times. So predict y hat given x. So to do that, we just simply plug in 1,000 for x, and we get approximately 77.63 degrees Fahrenheit. Okay, and what is the meaning of slope and y-intercept? Okay, so for the slope, remember we say for every 1 unit increase in chirps per minute, that's x, the temperature y hat will increase by 0.05 degrees Fahrenheit. And then for the y-intercept, remember that's just the response variable y hat when x is 0. And when it's 0 degrees outside, you could argue that these crickets here might not be around. So you could really argue no meaning on this one, but if it did have meaning, then you would say that the temperature when a cricket chirps 0 chirps per minute would be the meaning for the y-intercept.